Welcome to the AI Coach by Anil Nathu, your shortcut to being well-informed on the cutting edge of AI. Today, we're embarking on a deep dive into AI engineering by Chip Huyen. This isn't just another book. It's an absolutely essential guide for anyone serious about building and scaling real-world AI applications, really bridging that gap between, cutting-edge research and practical enterprise deployment.
It truly is a vital guide, yeah.
Yeah.
Especially given how fast generative AI is moving. Chip Huyen brings this unique depth of expertise, offering a really comprehensive, holistic approach. It covers everything from, initial model development and evaluation, all the way through to large-scale deployment. What's particularly insightful here, I think, is how the book helps bridge that common collaboration gap, between different teams, cross-functional
Well, look,
teams.
getting everyone on the same page.
Exactly, making sure everyone understands what goes into building these AI products. So our mission today is really to extract the most important nuggets from this work, give you practical guidance, and hopefully spark some of those aha moments.
Exactly. So you'll walk away from this deep dive with a thorough understanding of what it really takes to build AI products that can actually scale. Moving beyond just simple prototypes to robust, reliable systems, we'll be breaking down the core concepts from each chapter, elaborating on key examples, case studies, and hopefully delivering practical lessons you can apply directly. So let's unpack this crucial information from AI Engineering by Chip Huyen. The Rise of AI Engineering and Foundation Models, drawing from Chapter 1. Okay, let's start at the beginning. When we look back, the ChatGPT moment, it wasn't just about the models being huge, right?
No, not at all.
It was that explosion of entirely new applications they suddenly unlocked. It showed us that even a small bump in model quality could translate into just immense new possibilities for real-world products. It really shifted things.
And if you connect this to the bigger picture, a lot of the established principles for building AI apps, that they absolutely remain relevant. But the sheer scale and the, dramatically improved capabilities of these new foundation models, they introduce fresh opportunities, sure, but also significant challenges.
Right. New problems need new solutions.
Exactly. And they demand entirely new solutions. This book really zeroes in on that, the whole end-to-end process of effectively adapting these foundation models to solve complex real-world problems.
So let's talk about those real-world problems. The book highlights successful use cases, spanning both consumer and enterprise applications. What are some examples that really stand out that illustrate this new era?
Well, let's start with education. Think about how AI can now create personalized lecture plans, adaptive learning materials. A foundation model can summarize entire textbooks, generate tailored quizzes, multiple choice, open-ended, whatever you need, and even evaluate student answers with pretty impressive accuracy.
And the market impact is huge there.
Oh, undeniable. Remember, Chegg? The
Yeah.
homework help service. Their share price just plummeted. I think it went from like $28 down to $2 or something crazy.
Wow.
Simply because students just turned to AI for their assignments. It shows just how quickly these models can disrupt established markets, create, existential shifts for businesses.
That's a powerful example. And moving to conversational bots, it's not just simple chatbots anymore, is it?
No way. We're talking everything from general-purpose co-pilots to really sophisticated customer support agents. And beyond saving significant costs because they respond faster, more consistently than human agents, some teams are even using groups of these bots to simulate entire societies.
Really, to study social dynamics.
Yeah, it's a completely new paradigm for research.
Wild.
Indeed. Then you have information aggregation. Imagine an AI that can just distill complex ideas from vast amounts of data, summarizing your emails, Slack messages, news feeds, detailed research papers.
That Salesforce research found most people use it for summarization, right?
Exactly, 74% in their 2023 study. And on the consumer side, look at Google Photos. It already uses AI to surface images matching your search queries from your, massive personal library.
Making it possible to find that one photo from years ago.
Right, that one you thought you'd never see again, instantly.
And finally, for workflow automation, the applications seem just as transformative.
Absolutely. AI is automating mundane tasks like travel planning, lead management, invoicing, even data entry. But what's truly fascinating, I think, is how AI can even synthesize training data to improve the models themselves.
That's pretty meta. AI helping build better AI.
Exactly, a truly meta application. But, before you even think about building, this raises a really fundamental question, and it's one you need to ask critically.
Which is?
Is the application truly necessary? Is AI genuinely the right tool for this problem? Or is there maybe a simpler solution? And perhaps most importantly, do you have to build it yourself? Or can you just buy an existing solution that meets your needs?
The build versus buy decision.
It's huge. It often boils down to whether AI presents like an existential opportunity or threat to your core business, or if it's mainly a profit or productivity booster. That choice has massive implications for resources, for strategy.
That's such a crucial way to frame it. Chip Huyen also helps us think about the role AI plays in an application. Is it critical or complementary? Reactive or proactive?
Yeah.
Dynamic or static?
Right. Those distinctions matter a lot.
Like Face ID on your phone, that's critical AI, right? The app wouldn't work without it.
Exactly.
A Gmail Smart Compose is complementary. Gmail works fine without it, it just enhances the experience.
Good example.
And proactive features, like Google Maps, traffic alerts, they need incredibly high quality, otherwise they're just annoying. Because you're not explicitly asking for them right then.
Precisely, to avoid being intrusive.
And dynamic features like Face ID need constant updates as user data changes, unlike static features that might only need periodic updates. Understanding these differences really guides your engineering effort.
Yeah, absolutely. And the book then breaks down the AI stack into 3 layers: application development, model development, and infrastructure. Now, traditional machine learning engineering principles, still applicable for sure, but AI engineering introduces unique innovations, particularly at the application and application development layers.
That's where most of the new tools came from.
Yeah, those layers saw the highest growth in new tools and frameworks in 2023, right after ChatGPT and Stable Diffusion really took off. Surprisingly, the core infrastructure they're growing in scale, obviously, but they've remained conceptually pretty similar. Understanding foundation models, drawing from Chapter 2.
Okay, so we've seen what these models can do. Now let's unpack how these foundation models actually work under the hood, and crucially, what fundamental limitations we need to be aware of when we're building with them.
Right, getting into the
But
mechanics.
it all starts with pre-training, right?
Yeah.
That makes a model incredibly capable, but not necessarily safe or easy to use conversationally.
Exactly. It's raw potential.
That's where post-training comes in. It's all about aligning the model with human preferences. Though, as the book highlights, that alignment is far from foolproof.
Oh, definitely not foolproof. And a model is truly only as good as its training data. That's rule number 1. If we connect this to the bigger picture, you immediately see the impact of English dominance. Models like GPT-4, they perform significantly better in English across benchmarks like MMLU compared to, say, underrepresented languages like Telugu.
And just translating isn't enough.
No, translation isn't ideal. You lose information, you lose cultural nuances embedded in specific phrasing or pronouns. It's just not the same.
So this leads to a practical insight. For specialized tasks or non-English languages, you often need domain-specific models, right? Trained on carefully curated data.
Absolutely. Think about fields like drug discovery or cancer screening. Public data is scarce, highly specific. General-purpose models might just stumble over niche terminology or data formats. A custom approach is often essential to get the precision you need.
Okay, so architecturally, what's under the hood?
At the core of most foundation models is the transformer architecture, with its revolutionary attention mechanism. To really get how these models process information in parallel during input, pre-filling, sequentially during output decoding, understanding query, key, and value vectors is crucial.
Do you break that down simply?
Conceptually, the query is like asking a question. Keys help identify relevant information in the input, and values provide the actual data. This mechanism lets the model efficiently weigh and synthesize just vast amounts of input.
And transformers aren't the only game in town anymore.
Right. Beyond transformers, we're even seeing emerging architectures like Mamba. Some models interleave transformer and Mamba layers, and they're showing strong performance with a smaller memory footprint. That's a critical advance for practical deployment.
Okay, here's where it gets really eye-opening for me.
Yeah.
Model scale. We have these huge numbers, billions of parameters, trillions of tokens, FLOPs.
Yeah, the compute requirements are staggering.
Training a single GPT-3 run cost over $4 million, apparently.
Astro.
But what's fascinating, and a bit counterintuitive, is this phenomenon of inverse scaling, where more alignment training, which you'd think makes models better, can sometimes lead to less alignment.
Yeah, it's paradoxical.
Like, models trained for more alignment might weirdly express specific political or religious views more often.
Oh.
Or double down on biases they were supposed to lose. It's a complex challenge.
It really is. And if we connect this to the bigger picture, there are 2 really visible bottlenecks for scaling that are causing real concern.
Okay.
Training data and electricity. we're potentially facing a shortage of high-quality internet data. The rate training data set sizes are growing is far outpacing new data generation.
We might run out of good data.
Potentially. Plus, the increasing amount of AI-generated content in training data could lead to model collapse.
Model collapse.
Yeah, where models gradually forget original data patterns. They start outputting more common events, basically losing the ability to generate rare or nuanced information. This is a huge concern for the long-term performance of any AI system, including the principles driving, say, a sophisticated AI coach.
Wow. And the other bottleneck.
Electricity. It's staggering. Data center consumption could soar to maybe 20% of global electricity by 2030. That not only limits growth, it also significantly drives up costs.
Okay, so once a model is pre-trained, post-training becomes essential. Techniques like supervised fine-tuning, SFT, and preference fine-tuning, often using RLHF, reinforcement. Learning from human feedback, they're crucial for making models conversational, safe, and mitigating those biases from internet data.
Absolutely. Without that step, a pre-trained model might just, complete text like an old web page, not hold a conversation.
And the reward model is key to that.
Yes, the reward model, central to preference fine-tuning, is trained on human comparison data. What makes it effective is that it's just an easier task for human labelers to compare two responses and say, this one's better.
Easier than giving an absolute score.
Much easier. And it leads to more consistent, reliable data for alignment. OpenAI's labelers for InstructGPT, for example, got around 73% agreement when ranking responses, which is pretty high for subjective stuff like this.
This section on sampling is truly illuminating. It perfectly explains why AI outputs are inherently probabilistic, which leads to both incredible creativity and sometimes frustrating things like inconsistency or hallucinations.
Right, it's the randomness factor.
It's why you can give the exact same input and get slightly different outputs each time.
Exactly. And for practical guidance, understanding temperature is key. Higher temperature means more creative, potentially less coherent outputs.
Like 0.7 for creative stuff.
Yeah, around there is common. It encourages variety. Lower temperatures make outputs more consistent, maybe more boring, but predictable. Then there's top K and top ape or nucleus sampling. These let you dynamically select tokens. Top 8, for instance, focuses on the smallest set of tokens whose cumulative probability hits a certain threshold, like 0.9 or 0.95.
Which helps make outputs more contextually appropriate.
Exactly, especially in open-ended scenarios, gives you more diverse but still relevant outputs.
And for anyone building applications, getting structured outputs like reliable JSON or SQL is vital.
Absolutely critical.
The book digs into the techniques, prompting for structure, post-processing, and especially constrained sampling to guide the output format.
Right. And this probabilistic nature, it's what makes models exciting and adaptable, but it also means we must build robust workflows to mitigate inconsistency, maybe by caching or fixing sampling variables like temperature and seed. And you have to tackle hallucinations through strategies like self-critique or prompting for truthfulness.
Though just fixing the settings isn't the whole story, right?
Not really. Fixing settings is good practice, but the real challenge is building a system that people trust, even when things aren't perfectly deterministic. 3. Evaluation methodologies and AI systems, drawing from chapters 3 and 4.
Evaluation. Okay, this is often, hands down, one of the hardest challenges in AI engineering.
Agreed. Hugely important, often underdeveloped.
It's absolutely critical for success, yet investments in it often lag behind model and application development. Too many teams still rely on subjective, vibe checks or word of mouth.
Which introduces significant unnecessary risk.
Definitely.
Now, when evaluating language models, metrics like perplexity measure predictive accuracy, basically, how well it predicts the next word, the next token. However, perplexity can behave kind of weirdly after post-training. A model that gets better at specific tasks might actually show a higher perplexity.
So it's not always a direct measure of quality.
No, not always a direct proxy for application quality. Relying solely on it can be really misleading.
So we need to move beyond those basic metrics to evaluate more complex, open-ended responses. This involves things like functional correctness and various similarity scores.
Right.
For practical guidance, let's distinguish between lexical similarity that's measuring token overlap, like edit distance between bad and barred, or n-gram similarity.
Word matching, essentially.
And semantic similarity. That uses embeddings to capture the meaning of the text, right, using metrics like cosine similarity. This is about what the text means, not just the exact words used.
Right.
Crucial for nuance.
Absolutely. And what's truly fascinating and a growing trend is using AI to evaluate AI. often called AI as a judge.
Right.
Here, a larger, usually more capable model evaluates responses based on criteria you define, like relevance or quality. Platforms like OpenAI and MLflow even offer built-in criteria now. These AI judges can actually perform surprisingly well on classification tasks and discrete scoring. It offers a scalable way to get initial feedback.
But is it truly reliable? That's the big question.
It is. There are concerns. It can be a bit tautological, right? One AI judging another.
Yeah.
It also introduces significant costs. You could double your API calls, one for generation, one for evaluation. Plus, the judge's own output quality can vary.
And crucially, you can't always evaluate factual correctness just with preference.
Exactly. Asking an AI judge to pick between yes and no on, say, is there a link between cell phone radiation and brain tumors? Based purely on preference. Well, that could give you misleading signals if you use it directly for model training. Human oversight remains essential.
So at the end of the day,
You don't care about finding the best model in some abstract universal sense. You care about finding the best model for your specific application.
right, your use case.
Which means rigorously evaluating models against your unique criteria. This involves looking at both hard attributes, things like licenses, training data characteristics, model size, privacy policies,
A non-negotiable.
and soft attributes, accuracy, toxicity, factual consistency, things like that.
And the choice between open source and API models has its own trade-offs. Open source gives you more control, but needs more in-house effort for hosting, maintenance.
Right, more heavy lifting.
API models are easier to start with, but you're tied to their SLAs, their pricing.
Sensor lock-in, potentially.
Yeah. And a huge warning here. Beware of data contamination on public leaderboards.
Oh, yeah, that's a big one.
This happens when models are trained on the same data they're evaluated on. So you get these inflated scores that look great, but don't reflect real-world performance at all.
So public benchmarks, they can help filter out the bad models, sure, but they don't necessarily identify the best model for your specific application.
Which leads to a crucial takeaway.
You need a reliable evaluation pipeline. First, you absolutely must evaluate all components in your system independently.
Don't blame the LLM if the PDF parser failed.
Exactly. If a PDF-to-text tool fails to extract info correctly, you need to know that before you blame the language model downstream. Then, define clear evaluation guidelines. What is a good response for your specific use case and what isn't? Like LinkedIn discovered, a correct response like you are a terrible fit for a job application
Ouch.
isn't necessarily a good one if it's not helpful or user-friendly.
So what does this all mean for you, the listener? You need to tie your evaluation metrics directly to business metrics. If your chatbot's factual consistency is 80%, maybe that's fine for product recommendations.
But totally unusable for billing questions.
Right, where you need 100% accuracy. You need to identify that usefulness threshold for your specific application.
And finally, choose your evaluation methods and data wisely. Use multiple data sets. Use statistical methods like bootstrapping to ensure reliability. Avoid pitfalls like Simpson's paradox.
Where it looks better overall, but is worse on every subgroup.
Exactly. This kind of systematic, rigorous approach is really a core principle for building a robust, effective AI coach by Anil Nathu, Prompt Engineering. Drawing him Chapter 5.
Okay, prompt engineering. It's often dismissed as just, fiddling with words.
Yeah, prompt whispering.
But as Chapter 5 powerfully reveals, it's so much more than that. Think of it as the art and science of human-to-AI communication. It's deceptively easy to write a prompt, but incredibly hard to write effective ones that reliably get the behavior you want from these complex models.
Clarity is absolutely key.
Yeah.
You need to explicitly state what you want the model to do, right down to the scoring system for an essay or the exact output format you need, like JSON with these specific keys.
And providing examples is also essential, right, for in-context learning.
Definitely. It helps the model understand your intent by mirroring patterns from the examples, especially crucial for generating structured outputs. It's like showing a kid exactly what you want them to do rather than just telling them vaguely.
And simple tricks can make a big difference too, like role-playing.
Yeah, telling the model act as a financial advisor can dramatically shift its persona and response style.
And asking it to think step by step. Chain of thought.
Right, chain of thought prompting. That can significantly reduce hallucinations and improve logical reasoning. It actually came out almost a year before ChatGPT, showing how fundamental it is.
And this whole process, it's not linear, is it?
No, highly iterative. You'll constantly be refining, testing your prompts. And while there are AI tools now to help generate or tweak prompts, starting by writing your own prompts manually really helps you build that deep, intuitive understanding of the model's quirks and sensitivities.
Which is crucial for effective development.
Absolutely essential.
Now, here's where prompt engineering gets truly critical. Defensive prompt engineering.
Yeah.
AI applications face real security risks that can totally undermine their usefulness and trustworthiness.
Big time.
We're talking data leaks, generating harmful content like instructions for illegal stuff, service interruptions, massive brand risk. Remember Google AI suggesting eating rocks?
Or Microsoft's Tay chatbot going off the rails.
Exactly. These are real-world consequences of not having adequate defenses.
That's right. And prompt attacks like jailbreaking or prompt injection, they aim to subvert the model's instructions entirely.
Like jailbreaking.
Jailbreaking is tricking a model into ignoring its safety guidelines. Could be as simple as asking it to ignore the above and say, as said FJSFD, or much more complex.
And output formatting manipulation.
That's stealthier, hiding malicious intent in unexpected formats, like asking a model to write a poem about hot wiring a car. The model does the poem part, but the content is problematic.
Even more insidious is indirect prompt injection.
Right, where attackers inject malicious code or instructions into, say, public web pages.
And if your AI uses web search,
Exactly. An agentic system might retrieve that page, see the malicious instruction, and maybe suggest importing something that leads to malware installation on your system. It's like passive phishing. The attacker waits for your AI to come to them.
wow.
And information extraction is another huge concern. Data theft, privacy violations, copyright regurgitation.
Models can memorize training data.
Sometimes, yes, parts of it. Specific prompts might then trigger them to output private information they were trained on. Researchers like Carlini showed methods to extract memorized data from GPT-2 and GPT-3. It highlights the critical need for careful data handling and strong safeguards.
So for practical guidance on defense, what are the key mechanisms?
Input filters are crucial. Detecting and masking sensitive info like PII before it even hits the model prevents leaks. You can also implement systems for blocking suspicious fill-in-the-blank requests that might be used for data extraction.
And checking the output, too.
Absolutely. Using dedicated moderation models to catch unsafe content in the outputs is vital. Ultimately, you need comprehensive guardrails, input, output, system architecture. It's non-negotiable for building trustworthy AI, VRI, and agents. Drawing from Chapter 6.
Okay, so many tasks today need extensive background knowledge, right? More than fits in a model's limited context window.
Absolutely. That fixed window is a real bottleneck.
And this critical limitation is precisely why retrieval augmented generation, or RAG, has become such a cornerstone of modern AI apps.
Definitely. RG systems cleverly combine a retriever, which fetches relevant info from external databases, often your own proprietary ones.
Your knowledge base.
Right. And a generator, that's your large language model, which then uses this retrieved information to formulate a response. The genius of RG is it lets models use only the most relevant information for each specific query.
Which improves quality and reduces hallucinations.
Dramatically. And it also cuts down costs because you're sending fewer input tokens to the expensive LLM.
The book really highlights RG's value for applications needing precise, up-to-date info without the huge cost or impracticality of fine-tuning a model for every single fact, especially when data changes often.
Exactly. It's a pattern that emerged super quickly and got widely adopted for its efficiency and effectiveness.
So how does this retrieval mechanism actually work? How does it find the right info?
Well, retrieval works by ranking documents for relevance. There are two main approaches. First, term-based retrieval. This relies on lexical matching keywords using algorithms like TF-IDF or BM25, often found in systems like Elasticsearch.
So if you query transformer architecture,
It might bring up documents about the electrical device or the movie, not just the AI concept, because it's just matching keywords.
okay. And the other approach?
Second, and often more powerful, is embedding-based retrieval or semantic retrieval. This converts text into numerical representations embeddings, allowing the system to match based on meaning, not just keywords.
Understanding context.
Precisely. This relies heavily on specialized vector databases and clever approximate nearest neighbor (ANN) algorithms like HNSW and IVF. They group similar vectors together for super fast searches across massive data sets.
So there's a clear trade-off here, then. Semantic retrieval gets higher accuracy, understands context better.
Generally, yeah.
But it can be more computationally expensive
Yeah.
because you need to generate embeddings and do vector searches.
Correct. It's worth noting, though, BM25, the older term-based method, it often remains a surprisingly strong baseline. It's efficient and works well for many things.
Okay, so how do we make RAG even more effective? What are the optimization techniques?
Several good ones. Re-ranking uses a more precise, but usually more expensive mechanism to refine the results from an initial, cheaper retrieval, like a second, smarter filter.
Okay.
Then there's chunking strategy, how you split your documents into smaller or larger chunks for retrieval. Small chunks offer maybe more diversity in results, but can lose crucial context.
While larger chunks keep context but might be less specific.
Exactly. Finding that right chunk size is often an art. Depends on your data.
And query rewriting seems incredibly important, especially for messy conversational queries.
Oh, vital. Like in a sales chat, if a user just says, "How about Emily Doe?" An AI model can smartly rewrite that into something specific like, "When was the last time Emily Doe bought something from us?"
And the AI can do the rewriting itself.
Yes, models are getting good at that. Finally, context augmentation. Adding useful metadata like titles or summaries to your chunks helps the retriever understand their relevance better, or even adding explicit questions each chunk can answer.
Okay, so moving beyond a RAG, AI agents promise something even more sophisticated.
Right. An AI agent processes a task, dynamically plans a sequence of actions, and then determines if the task is done. It's essentially giving AI the ability to think, act, and course correct autonomously using different tools.
So what are the key components of these agents?
They include tools like web search, calculators, SQL executors. They need memory systems to recall past interactions. They need sophisticated planning capabilities, and the ability for reflection to learn from mistakes.
And can they really plan?
Well, some researchers debate if foundation models truly plan like humans, but agent frameworks like React, that's reasoning plus acting, they explicitly prompt models to think step by step, show their work before taking action. And that transparency has led to big performance improvements.
And for agents to be truly useful, they need memory.
Right, absolutely critical. We're talking 3 types. Internal knowledge, what the model was trained on, short-term memory, the current conversation's context window, and crucially, long-term memory.
That's the external storage.
Exactly. External systems like vector databases, relational databases, knowledge graphs, designed to persist information across multiple sessions.
And that long-term memory is essential for a lot.
Oh, yeah. It enables personalization. Imagine your personal AI coach remembering all your past interactions, your preferences, your learning style.
That would be powerful.
It ensures consistency, so the AI doesn't give different answers to the same question over time. It helps manage information overflow within long sessions. And it's vital for maintaining data structural integrity for complex, evolving knowledge. Effective long-term memory is really central to the vision of a truly intelligent, helpful AI assistant. Fine-tuning. Drawing from Chapter 7.
Okay, so we've talked about what these models are, how they use external data with a RAG. But what if you need to adapt a foundation model to your very specific needs, beyond just prompting or giving it documents?
Right, when you need to change the model's inherent behavior or knowledge.
That's where fine-tuning comes in. Chapter 7 digs deep into this. It's basically an extension of the original pre-training, letting you imbue models with more specific knowledge or behaviors.
But when to fine-tune is a really critical decision because it requires significantly more resources, data, specialized hardware, ML talent than prompt engineering or even RG.
A bigger commitment.
Much bigger. So it's generally attempted only when those other methods just aren't cutting it. And it's nuanced because, surprisingly, sometimes a big general model like GPT-4 can actually outperform a specialized model like Bloomberg GPT on financial tasks right out of the box.
Really? Even on specialized tasks?
Some research has shown that, yeah. But fine-tuning can still offer distinct advantages for very specific scenarios where general models fall short.
This leads to a really crucial distinction the book emphasizes. Fine-tuning is for form, RAGs for facts.
That's a great way to put it.
RAG gives models external knowledge for factual accuracy by retrieving info. Fine-tuning, on the other hand, is more about teaching models to understand and follow specific syntaxes, styles, output formats.
Exactly, like generating HTML code reliably, or specific JSON structures, or writing in a very particular company tone.
So if you have both information issues and behavior issues.
The book wisely recommends starting with RAG because it's usually much easier to implement and get working effectively than curating the high-quality data needed for good fine-tuning.
Okay. Now, fine-tuning large models is incredibly memory intensive. Why is that?
Well, partly the sheer size of the model weights, obviously, but also the activations, the gradients, the optimizer states, all these things need to be stored in memory during training. For example, updating all parameters in a 13 billion parameter model using the standard Atom optimizer.
Okay.
That can require something like 78 GB of memory just for the gradients and optimizer states, not even counting the model weights themselves.
Wow. That's a lot of memory.
It is, and this is where numerical representations play a huge role. We talk about FP32, single precision, FP16, half precision, BF16.
Different ways to store the numbers.
Right. And quantization is a key technique here. It reduces the number of bits needed to represent these values, which significantly cuts down memory usage.
Making it more efficient.
Hugely. Imagine the core principles of an AI coach running efficiently even on, say, your phone, thanks to these optimizations. Microsoft's BitNet B1.58, for instance, amazingly uses only 1.58 bits per parameter, but performs comparably to a 16-bit Llama 2.
That really democratizes fine-tuning, makes it more accessible.
Absolutely. And to tackle these memory challenges while still getting strong performance, many fine-tuning techniques have emerged. Parameter-efficient fine-tuning, or PFFT, is a broad category focused on reducing the number of parameters you actually need to train.
And LoRa is a popular one, low-rank adaptation.
Extremely popular. LoRa works by injecting small trainable matrices adapters into the transformer architecture while keeping most of the original huge model frozen.
So you only train the small bits.
Exactly. This dramatically reduces the memory footprint and the computational cost during fine-tuning.
And what makes LoRa really appealing is that these small LoRa adapters are modular and shareable. You see them all over platforms like Hugging Face.
Right. It allows people to easily combine and reuse fine-tuned capabilities. And often a very small rank for these adapters, maybe between 4 and 64, is enough for many tasks. Much smaller memory footprint than fine-tuning the whole model.
Building on that, there's QLoRa, quantized LoRa.
Yes, QLoRa takes memory efficiency even further. It stores the main model weights in just 4 bits, but then dequantizes them back to BF16 for the actual computation, squeezing out even more memory savings.
And finally, model merging.
Yeah, that's a more experimental but really promising approach. You basically combine multiple fine-tuned models, maybe models trained for different tasks or styles, into a single unified model.
What's the use case for that?
Could be great for multitask learning, or for optimizing models for on-device deployment, where you need one compact model that can do several things. Techniques involve things like summing weights, stacking layers, or concatenating parts of models. Still early days, but very interesting. 7. Dataset engineering, drawing from Chapter 8.
Okay, this next point is absolutely foundational. We've touched on it before. The quality of a model is entirely dependent on its training data.
Can't say it enough. Garbage in, garbage out.
As Chapter 8 constantly reminds us, even the best ML team on Earth can't fine-tune a good model without good data. This is precisely where dataset engineering comes in and why it's so critical.
And a crucial insight here is that a small amount of high-quality data can often outperform a massive amount of noisy data.
Quality over quantity.
Absolutely. The creators of the Yi model, for instance, found that just 10,000 carefully crafted instructions were superior to hundreds of thousands of noisy ones they collected initially. Beyond just volume, data needs to be meticulously aligned with user intent. It needs to be consistent across annotators. You don't want different labelers giving contradictory signals. And critically, it needs to be diverse.
Diverse in terms of topics, speaking patterns.
Exactly. If there's too little diversity, models will just struggle when they encounter new, unseen scenarios out in the real world. They overfit to the narrow training data.
And regarding data quantity, you hit diminishing returns pretty quickly, right?
You do. The first 1,000 examples you add might boost accuracy by, say, 10 percentage points, but the next 1,000 might only give you 5 points, and the next 1,000 maybe only 2.
So the focus shifts from just collecting more data to getting higher quality data.
Precisely. That becomes the bottleneck. Now, when human-generated data is scarce or maybe just doesn't exist for certain niche scenarios, synthetic data can be a real game changer.
AI generating training data.
Yeah. It can significantly increase data coverage. It can improve quality AI, can generate far more complex math problems than humans typically write, for instance. DeepMind's alpha geometry was trained on 100 million synthetic examples.
Wow.
Or it can overcome human limitations in data creation, like generating highly specific data for how an AI should use a particular tool.
Okay, but this is where it gets kind of unsettling, right? That model collapse idea.
Yes, it's a significant concern and vital to understand. Recursively training new AI models on AI-generated data can cause them to gradually forget the original data patterns.
I start repeating themselves.
Kind of. Over time, models might start producing more generic, lower quality outputs. They forget rare or unique events and patterns from the original human data. Their performance degrades. It's a fundamental challenge for the long-term viability of AI, including, potentially, the principles driving your future AI coach.
So how do you mitigate that?
Researchers are actively exploring it. A key strategy seems to be strategically mixing synthetic data with high-quality real data, not relying solely on synthetic stuff.
Makes sense.
And regardless of how data is generated, human, synthetic, whatever raw data needs extensive processing, this isn't optional.
What does that involve?
Meticulously inspecting it for quality, diligently deduplicating it, and that means whole documents, paragraphs, even checking across documents for overlap, cleaning out irrelevant or noisy parts, filtering for relevance to your task, and carefully formatting it so the model can actually use it.
This makes that quote from OpenAI's Greg Grockman really hit home. Manual inspection of data has probably the highest value to prestige ratio of any activity in machine learning.
It's so true. Just staring at your data for 15 minutes can often save hours of debugging headaches later. You spot inconsistencies, biases, formatting errors that would otherwise totally derail your model.
And deduplicating is critical too.
Absolutely critical. You need to avoid skewed distributions in your training data, and crucially, prevent test set contamination, ensuring your evaluation data hasn't accidentally leaked into your training data, which would give you falsely optimistic results. Good dataset engineering ensures your evaluations are truly meaningful. 8. Inference optimization, drawing from Chapter 9.
Okay, so you've developed, you've trained, you've fine-tuned this amazing model. The next crucial step, how do you actually use it efficiently in the real world?
Right, making it practical.
That's what inference optimization is all about. Taking your trained model and making it compute outputs for inputs as quickly and cost-effectively as possible. Chapter 9 gives a fantastic deep dive here.
So an inference server is basically what hosts your models and intelligently allocates the compute resources GPUs, usually. When thinking about performance, it's important to understand the bottlenecks. Pre-filling that's processing your input prompt is typically compute-bound. It needs raw processing power. In contrast, decoding generating the output token by token that's often memory bandwidth bound. It depends on how quickly you can move data on and off the GPU memory.
And for language models, especially in streaming mode like chatbots, what metrics really matter?
We particularly care about two key performance metrics. Time to first token, TTFT.
How quickly the first word appears.
Right, measures initial responsiveness, crucial for chatbots feeling instant, and time per output token, TPOT.
How fast the rest of the words come out.
Exactly, indicates the subsequent generation speed. A TPOT, around 120 meters per token, maybe 6 to 8 tokens per second, is usually fast enough for comfortable reading.
And beyond the user experience, there's system efficiency too.
Right. We also look at model FLOP's utilization, MFU. That's the ratio of your observed throughput to the theoretical maximum throughput of your hardware. Basically, how effectively are you using those expensive GPUs?
Got it. So how do we optimize? Let's start with model optimization techniques. These modify the model itself.
Correct. Modifying the model itself for efficiency, ideally without hurting output quality too much. Model compression is one approach. That includes pruning.
Removing less important parameters.
Yeah, removing connections or weights deemed less important. Or distillation, where you train a smaller student model to mimic the behavior of a larger teacher model.
Is pruning common?
You know, while pruning can reduce non-zero parameter counts by over 90% sometimes, it's actually less common in practice than you might think. It can be complex to implement well, and the real-world performance boosts aren't always as big as hoped. Distillation is often more practical.
Okay. Now, a key bottleneck in LLMs is that autoregressive decoding, right? Generating tokens one by one.
Huge bottleneck, inherently sequential.
This is where speculative decoding comes in.
Yeah, it's a really clever technique. You use a smaller, much faster draft model to guess several future tokens in advance.
And the main model checks the guesses.
Exactly. The main larger model then quickly verifies these guess tokens in parallel, much faster than generating them itself. This can significantly speed up generation by turning that sequential process into more of a parallel verification step.
Clever. What about optimizing the attention mechanism itself?
Also crucial. Efficiently managing the KV cache, that storage for key value pairs from previous tokens, is vital, especially for long contexts. Techniques like multi-query attention, where all query heads share the same key value pairs, or grouped query attention, where heads are grouped to share pairs, can drastically reduce the memory needed for that cache.
Which allows for bigger batches.
Exactly, making it feasible to process much larger batch sizes, improving throughput. Character.ai, for example, reportedly cut their KV cache memory by over 20 times for long chats using these kinds of techniques. Huge impact.
Okay, so those optimize the model. What about inference service optimization? Managing resources without changing the model.
Right. These techniques manage your resources better. A fantastic piece of practical guidance here is batching, processing multiple user requests simultaneously.
The bus analogy.
Exactly. Fill a bus instead of sending individual cars. This significantly increases your overall system throughput. It might add a tiny bit of latency for individual requests, but usually negligible if handled smartly with techniques like continuous batching.
And prompt caching seems incredibly powerful too.
Oh, massively powerful. It stores overlapping text segments, think system prompts, or long documents that users query repeatedly for reuse.
So the model only processes them once.
Right, saving significant compute. This can dramatically slash both latency and cost. Anthropic found that chatting with a 100,000 token book saw a 79% cut in time to first token and a massive 90% cost reduction with effective caching.
Incredible savings. And to truly scale big systems.
Parallelism is essential. Splitting the workload across multiple machines. You have data parallelism, running multiple copies of the model on different data, and model parallelism, which splits the same model across machines.
How does model parallelism work?
Different ways. Tensor parallelism splits the big matrix multiplications across devices. Pipeline parallelism breaks the model into sequential stages, putting different stages on different machines. These complex techniques are what ensure something like an AI coach by Anil Nathu can truly deliver insights at scale, handling tons of requests efficiently. AI engineering architecture and user feedback, drawing from Chapter 10.
All right, finally, let's talk about putting it all together. The overall architecture of a real-world AI application and the absolute crucial role of user feedback. Chapter 10 really ties everything into a cohesive picture.
Yeah, moving from components to the whole system. A simple architecture just sends a query to a model, gets a response back, but real-world apps build way beyond that.
Starting with context augmentation.
Right, giving the model access to external data sources, RAG, and tools like web search, calculators, APIs. It's like giving your AI a bigger brain and a toolbox.
And guardrails seem non-negotiable.
Absolutely essential for both safety and quality. Input guardrails detect and mask sensitive info, like PII, before it gets sent to external APIs, preventing leaks.
And output guardrails.
Output guardrails catch failures or unsafe content, toxic responses, factually contradictory stuff, protecting your users, your brand, ensuring quality, critical for any production system.
Then there's the model router and gateway.
Yeah, think of it as an intelligent traffic controller. It directs queries to the right model, maybe based on user intent or for A/B testing different models. It also adds security layers, helps manage costs by picking the cheapest effective model.
And caching we talked about, crucial for latency and cost.
Fundamental. Exact caching reuses identical responses. Semantic caching is more advanced, reuses responses for semantically similar queries.
But trickier to get right.
Much trickier. Requires careful threshold setting, can fail unexpectedly if the semantic similarity check isn't robust, more complex.
And beyond just RAG, we have agent patterns for more complex workflows.
Right. For tasks needing loops, parallel actions, conditional logic, an AI agent might decide it needs to do another retrieval or use a specific tool, creating a dynamic loop until the goal is met.
And orchestrating all this complexity.
That choreography often relies on specialized AI pipeline orchestrators like LangChain or Lemma Index. They help define and manage how all these components, retrieval, generation, guardrails, tools work together.
So once it's live, how do you know what's really happening?
That's where monitoring and observability come in. You absolutely need to track comprehensive metrics, factual consistency, response quality, safety flags, cost per query. You need detailed logs. You need traces to follow requests through the system and debug issues.
Interdetection.
Particularly important, helps you spot when your model's performance unexpectedly changes or degrades in production. Is it still meeting that usefulness threshold you defined? You need to know.
Okay, now let's talk about the absolute goldmine,
Hmm.
user feedback.
Invaluable, truly.
It's not just crucial for evaluating real-world performance. It generates proprietary data. That's a critical competitive advantage for continuously improving your model.
Exactly. It creates that powerful data flywheel.
Yeah.
Launch fast, get users, gather their feedback data, use that unique data to improve your models, which attracts more users, and so on.
And we distinguish between explicit and implicit feedback.
Right. Explicit feedback is direct. Thumbs up, down, star ratings, maybe editing the response. Implicit feedback is inferred from user behavior. Do they engage with the response? Do they immediately rephrase their question, indicating confusion? How quickly do they respond?
Implicit seems harder but richer.
Generally, yeah. Harder to extract and interpret reliably, but can provide deeper signals about true user satisfaction or points of friction.
So when designing for feedback, when's the best time to ask for it?
Good question. Often best when the model itself has low confidence. Maybe it offers multiple options and asks the user to choose the best one, like Google Photos asking, "Is this your cat?"
Or when something goes wrong.
Critically, yes. When something clearly fails, that's a prime opportunity. But avoid asking for positive feedback too often.
Why is that?
It can give users the impression that good results are rare exceptions. And people are generally less likely to provide feedback if it requires extra effort, especially if things seem okay.
Okay, now this is where user feedback gets really nuanced and fascinating. It's not perfect. It comes with its own biases.
Oh, definitely. Lots of them. Like leniency bias. People often rate things more positively than they perhaps should, maybe to avoid conflict or just finish the task quickly.
And position bias.
Users are much more likely to click the very first suggestion or result they see, regardless of its actual quality compared to the others, just because it's first.
And preference bias.
People might prefer longer responses, even if they're less accurate, just because they seem more comprehensive, or they might favor the last answer they saw due to recency effects.
Understanding these subtle biases is absolutely crucial then. For interpreting feedback correctly and avoiding misleading product decisions based on flawed signals.
Exactly. This is precisely where the practical insights and rigorous approach championed by something like an AI coach by Anil Nathu truly make a difference, helping you build more robust, user-centric, and ultimately more successful AI systems by navigating these complexities. Outro.
And that concludes our deep dive into AI engineering by Chip Huyen. What a truly comprehensive guide for navigating the complexities of building and scaling real-world AI applications. We've covered so much, from fundamental concepts like foundation models and their limitations to practical guidance on evaluation, prompt engineering, R-Edge, agent fine-tuning, dataset engineering, and those essential inference optimizations.
Indeed. This book offers really timeless foundational knowledge. It's essential for both product managers and engineers who want to excel in this rapidly evolving field. It does such a good job bridging that collaboration gap between cross-functional teams, making it a must-have resource for anyone serious about building production-ready AI. The core principles it outlines for building scalable, reliable AI are paramount. Even as the specific models change rapidly, having this solid engineering foundation is what matters.
Absolutely. Thank you for joining us today. Buy the book at the AI Coach website for more insights on artificial intelligence.